Welcome to this video. My name is Mark Scythian. The date today is May 21st, 2025. In this video, we're going to focus on light bulb resistance across a DC parallel circuit. In the previous video, we focused on light bulb resistance across a DC series circuit. So a parallel electrical circuit maintains constant voltage, whereas a series electrical circuit maintains constant current or constant amperes. So we can identify 12 volts at each light bulb because our source battery voltage is 12 volts, and then we have our Ohm's law formula here. E is voltage is equal to current times resistance, only in DC circuits. And then DC electrical power in wattage is P is equal to I current in amps times E volts. Voltage and volts and voltage. So E is the voltage, I is the current in amperes, and when we multiply these two out, volts times amps, we get DC electrical power measured in watts. So for light bulb number 1, we can rearrange the wattage formula to solve for current. So we can divide the wattage of light bulb number 1 into the voltage and calculate 1.46 amps of current at light bulb 1. So this then allows us to solve for resistance by rearranging the Ohm's law formula to solve for resistance. We simply just divide the voltage into the current to solve for the resistance. So 12 volts divided into 1.46 amps. And then we calculate 8.2 ohms as the resistance for light bulb 1. So we can follow suit for the next two circuits, light bulb 2 and light bulb 3. However, when we get to light bulb 4, we have to be very careful now, because even though all 4 light bulb circuits are energized in parallel, when we do the circuit analysis, the end pathway is obeying a series pathway with respect to circuit analysis. So we must identify this as a series pathway and emphatically identify that. So series pathway, be advised. And this is where most, if not all, students or those solving technical problems make a big mistake, and then they end up needing to go back to equipment, and then they end up having to waste a lot of time, and it just could have been solved right there on the spot when you look at the schematic and you look at the actual product or equipment. You can say, wait a second, this is a series pathway. So what we have to do is kind of ignore the voltage there, because we're really going back to this E is equal to IR in series, and in parallel it would be I is E over R, because in series we have constant current, so we multiply that times resistance to get voltage. In parallel circuits we have constant voltage, so we can divide the voltage into the resistance to solve for the current draw or the current drop in the parallel instead of the voltage drop in series. So when we combine all these circuits, we're actually going to multiply a certain amperes times the resistance to get then the voltage here. So this is like the answer, but we don't know the root of that answer. So what we can do is just go ahead and solve for current as we would usually solve for current. 100 watts divided into 12 volts, 8.33 amps. So now we have to apply Ohm's law for series pathways and DC circuits, so we can just rearrange it for resistance. And then we calculate 12 volts divided by 8.33 amps. So we approximate 1.4 ohms of resistance at light bulb 4. But now we have to test/check to see if that's actually accurate. So if you can quickly calculate DC circuit values, you could actually troubleshoot electronics super fast with or without a multimeter. To an extent, you might have to check for grounds, you might have to check for continuity, etc. And those assumptions are proven as true, but you can pretty much cut to the circuit pretty quickly. So this is the training part. So after you understand the fundamentals, you probably don't have to keep checking. But just to make sure this is accurate and it's not just another video, it's actually usable data, is that we can go back and check our work. And so we know the total resistance of the circuit is the total voltage divided into the total current. So we'll just enter those in as 12 volts total voltage, and then we can actually add all of the current drops at each circuit in parallel as a cumulative function to calculate the total current. So we calculate 18.49 amps, and so we can divide the total voltage into the total current, and then we calculate 0.65 ohms as the total resistance of the entire circuit. So if you put your ohms meter from our positive point to our negative point while it's energized, or better yet from the output. So DC electrical circuits have electron travel only from positive to negative. So it keeps going positive, negative. So you could put your ohm meter on, let's say, the first junction here, and then the ground junction here, and then you'll get 0.65 ohms while the pathways are energized. So we've calculated the total resistance. So now we can use the inverse sum law of simply taking the reciprocal of every ohms value, 1 over 8.2 for light bulb 1, plus 1 over 4.1 for light bulb 2, 1 over 2.1 ohms for light bulb 3, and then 1 over 1.4 ohms for light bulb 4. And we can add up these fractions and then find the inverse, so 1 over the answer. So when you take just the parentheses contain fractions of the reciprocal of each ohms value and you add them together, you then find the inverse, or 1 over that. So when you figure that out, you'll get 0.6425. And so of course we rounded the resistance for light bulb 4 down. It should be 1.44. So this is approximately the same as the total resistance as calculated by total voltage into total current. So this is the correct valuation. Now if you treated this as just another parallel pathway, you'll get a value that is a little higher. And then when you combine these resistances in parallel, you get a value that's twice as large as this total resistance value. So in actuality, the calculation was wrong. 1.8 something is wrong. And then you're like, what's going on here? Well, you have to treat the N return pathway as a series pathway with respect to circuit analysis. But when it's energized, then you can just treat all four as a parallel energetic relationship. So that's the little bit of a tricky part here, but you have to be careful. So if you start working with series parallel pathways, then you'll know this potential stumbling block. So treat the N circuit as if it is a series pathway when you do the circuit analysis. So we've proven the resistance value at light bulb 4 is indeed 1.4 ohms. So now we can present the final schematic, and this would be certified information So if you made any design or modifications to the product, you can then enter this in as the certified information. And so sometimes you can't just rely on what's in the book, and you sometimes can't rely on what is just in the multimeter ohms reading. You may have to look over the schematic and then individually test your ohm meter from positive to negative here. And let's say the information is validated as correct, you should be getting 1.4 ohms on your ohm meter. So let's just say that did happen. You could rule out the circuit as being discrepant. You could ignore it. It's not discrepant. And then you go across, take the multimeter reading on light bulb 3 positive to negative, and you get 2.1 and so on and so forth. So you may have some other issue like a switch to ground, or you may have perhaps there's nothing wrong with the circuit. Maybe it has to be inspected and you can validate it as unremarkable or no discrepancies. But sometimes other issues other than the electrical wiring, perhaps electromagnetic interference, etc. But you can rule out the hardware as having zero or no discrepancies and then move on to something else. But you can do this really quickly. So if you're working with electricity, electronics, electrical analysis, subscribe to my channel, and I'm going to be posting more videos, not just on circuit analysis, but many troubleshooting tips with multimeters, how to quickly assess electrical and electronic circuits in both AC and DC circuit analysis. So feel free to subscribe and stick with me on this channel, because I'm going to be releasing much more electrical and electronics information for circuit analysis and training, etc. Skilled trades, tech, and electrical engineering as well, across both the hands-on and the design paradigms. Thank you for watching this video and have a great day.